Hello students, in this video we are going to study about Bernoulli's principle. The previous videos we studied about steady flow and turbulent flow, and we moved on further to there are three types of energies in a liquid flow. We studied that, and we also studied about equation of continuity that states that A1 V1 is equal to A2 V2, where A is the area of cross section and V is the velocity with which it is flowing. So this we did this, and today we are going to discuss about Bernoulli's principle and derive the equation for it. Now I have taken a tube with varying cross sectional area. Now this is a large part here, and let us say the area of this part is A1, right? This is A1, the large part, and I have a narrow section here, and this as an area A2, area of cross section A2. You know very well A1 is greater than A2. That is the first condition. Now through this we are going to allow a liquid to flow. And what type of liquid? It is an ideal fluid, ideal liquid. And what are the conditions for a liquid to be ideal? One, it flows, steady flow is there in that, and then it is non-viscous. We assume that there is no internal friction, and then it is incompressible. That means uniform density, and the density I have taken here as rho, and steady flow. These are the main factors that it is an ideal fluid. Now we already discussed about Bernoulli's principle that the pressure energy and the velocity energy and the potential energy are all added together is a constant. That is what we are trying to now prove by this. Okay, now let me take this end here. This end is A and the other end is B. Okay, liquid is flowing from this part to the upper part like that. Okay, so what I should do? I have to apply a force. I am applying, imagine I have a block like that, imagine like that, right? I am applying a force on the liquid, right? And that liquid is going to flow now, right? Now when it is flowing, I apply a force here, F1. Now what is force in terms of pressure? We know that pressure is equal to force upon area. Force upon area, we can say force is equal to pressure into area. Okay, now in this F1, so that is pressure 1 at this point and A1 at this end A. So P1 A1 is the force applied at this point. So when we apply force, what will happen? The liquid will move. As if the liquid is moving up, let us come to the narrow section. At the narrow section B, what is the force coming out here? What is the force acting here? That is P2 A2. Now I have taken this much of liquid here, the quantity I have taken this much, and that I have spread it like this. So this is little larger because narrow pipe, the same quantity is coming here, this quantity is replaced here as this quantity. Fine. Now we will calculate what is the, let us say this is the ground level. This is the ground level. At the ground level, from the ground level, the point A, the middle point of it is lying at a height H1, and the point B here, it lies at a height H2. There is a varying height, right? Varying cross section. Fine. Now I apply a force and move it. Now we have to find out what is the different energies, right? I am going to do work now by pushing it from here to here. So what energies will come into play? When I push an object, kinetic energy will come. So we will first study about kinetic energy. Okay, kinetic energy. Now what is the formula for kinetic energy? Half kinetic energy is equal to half mv square. Velocity at this end is v1 and velocity at this end is v2. Okay, now what is the difference in kinetic energy? Difference in kinetic energy is final kinetic energy minus initial kinetic energy. Okay, so I will write here the discussion of kinetic energy. Change in kinetic energy is equal to kinetic energy final minus kinetic energy initial, which is equal to half mv square, and final v2 square minus half mv1 square. Mass is same. Why? The amount of water which we are discussing about is same amount. The quantity is same, right? That is why I have taken same mass. Okay, that is equal to half is common, m is common, v2 square minus v1 square is the next step. Now we will write what is mass in terms of density. You know, I will write here mass is equal to R. Density is equal to mass upon volume, or mass is equal to density into volume, that is equal to density into volume. We are talking about area, so we have to express in terms of area. So we will say area into length with which it is moving. What is the distance it is moving? Okay, distance it is moving. So you can put A into D if you want, no problem, right? That is equal to rho into A into. Again, we express the distance to travel in terms of velocity, right? And we know that velocity is equal to distance upon time. Distance is equal to velocity into time. Velocity at this point is v1. So v into delta t, I am going to say. V into delta t. Delta t, why? We are measuring for a small amount of time. Now what is the time I have taken here for this area at this point A? A time, let us say 1 second, 2 second, whatever the time I have chosen. I am studying for the same time how much quantity is moved, all the factors. So time is kept here as a constant. All the factors are changing, right? So you see the distance, length, traveled is changed, distance is changed, but velocity also is different, but time is a constant. I study for the same time, 1 second, 2 second, how much it is moved in the other end B. That is what I am doing. Okay, fine. So what I am going to do, that is equal to half into mass can be written as rho A V delta T. Okay, so this I have taken as a constant. If you want, I can put rho 1, A1, V1 and all that. Instead of that, I have taken is there a constant, and I will tell you what the reason for that, and I will justify it in the later part of it. Okay, so V2 square minus V1 square, this is the formula. So what is the formula for kinetic energy? Half rho, density of the liquid is same, area of cross section is different, but I will justify why I have dropped the subscript. Okay, A1 V1, let us say, no issue. Here itself I will explain. A1 V1, we know according to the equation of continuity, A1 V1 is equal to A2 V2. Same, yeah, according to continuity, area of cross section into velocity at A, area of cross section and velocity at B, they are equal. So simply I can write it here as A into V. This is a easy method which I found it will be better for you, right? So don't bring the subscript, because once you say that initially according to equation of continuity, where the flow is due to ideal fluid, then where it is non-viscous, incompressible, steady flow, all these are irrotational. Yes, that is another word which I have forgotten, irrotational. When all these factors are 0.1, 2, 3 and 4 is satisfied, when equation of continuity says A1 V1 is equal to A2 V2 is equal to A into V. So that is what I have taken. I have dropped the subscript. Dear students, you know delta T is same, time is being same, so I have kept it as it is. Okay. So my board, I need to erase this. Dear students, yeah, as you are watching in the video, you can always turn it back and come back and see it again. Okay, so I will take only the final result. Change in kinetic energy is equal to half into rho into A into V into delta T into V square V2 square minus V1 square. Okay, so let me erase this here. Let me make it here equal to A into V. Okay, fine. One is kinetic energy. The force I apply pushes the water, that is kinetic energy. Next is potential energy. Potential energy, right? Both are at different heights from the horizontal ground level. So, I will say change in potential energy is equal to potential energy at the point B minus potential energy at the point A. That is equal to mgh2 minus mgh1. Fine. So, I think I can use this step if I possible, right? So, that is equal to mg is common, h2 minus h1 is the difference. That is equal to m. In the place of m, what we do? Rho A V delta T. Again, use the principle of continuity. A into V is one and the constant. So, we will take it from here, H2 minus H1. This is the second equation, and that is for potential energy. So, watch it carefully. The potential energy at this point is mgh2 minus mgh1, right? So, this is what I have done here. So, let me take the final result. Change in potential energy is equal to rho A V delta T. Yes, I forgot a term here, that is G. Okay, this G is there. G. Okay, G rho. Okay, start with G rho. Right. H2 H1. 0, not 0. Zero. Easy to remember. Make some acronyms. Okay. 0, 0, 0, 0. Right. Having found these two factors, kinetic energy and potential energy, we now go to work done. What is the work done in pushing this water, quantity of water from this point A to this point B? So, my discussion here is work done is equal to, this is the external work done. This work done is transferred into kinetic energy and potential energy. What is the formula for work done? Force into displacement. Okay. Now, what is force in terms of pressure? Pressure is equal to force upon area, which implies F is equal to pressure into area. Okay. I will put here pressure into area into distance. Okay. So, after that point, let me erase this here. Again, you have the same thing here also. So, what is the distance traveled? What is the distance traveled? That is PA into velocity. Have I written here? Velocity is equal to distance upon time. Distance is equal to velocity into time. Time is a small amount, delta t. So, velocity into delta t. So, I will put it V delta t. Yes, I have got this equation, that is AV delta t. This is the work done formula. Now, we need to compare the work done and equal to change in potential energy and kinetic energy. I hope now I can erase this part of it. Okay. I want to tell you a point here. Before erasing this, there are 2 points are there. Pressure 1 is here and pressure 2 is here. So, we have to make the work done is equal to pressure. Difference in pressure. Where initially the pressure is more here. See, the pressure is more here. That is why the water is going upward. The pressure is more here, the force is more here. If not, the water will come down due to the gravity. But the pressure is more here, that's why it is pushing the water upward. So P1 is greater than P2. So difference in pressure, I have to write here difference in pressure, which is P1 minus P2 of AV delta T. I hope you understand. Work done is by moving the liquid from the point A to point B, from a broader cross section to a lower cross section, from a smaller height to a higher height. Then the force here will be more. Then it pushes the water up and all the things happen. So work done is equal to, external work done is equal to difference in pressure, we are expressing in terms of pressure, into area of cross section, right? V, that is the velocity with which again we say A1 V1 is equal to A2 V2 is equal to AV according to principle of continuity. Now let me erase this part, right? The whole Bernoulli's theorem or Bernoulli's principle is based on an ideal fluid which is incompressible, irrotational, steady flow, and 3-4 factors were there, non-viscous. Okay, so these are the factors we have taken. Yes, let me erase this properly. Okay, I think I can erase this also. Is all mere substitutions. Yeah. Okay, fine. So let me continue with the discussion. The external work done is used to change the kinetic energy plus change in potential energy. Okay, that is AV delta T of P1 minus P2 is equal to kinetic energy half rho AV delta T of V2 square minus V1 square plus, right? Oh my God, G rho AV delta T, let me erase this part now, into H2 minus H1. Let me erase all this part now. Okay, fine. Yes, dear students, looks very long. Try to understand conceptually. Very simple point I will tell you. There is a tube which is of non-uniform cross section. That's all. This is the only thing you should remember. This is of non-uniform cross section. In this, the liquid is flowing. And we study in this what is the force you apply, and you study what is the force with which it is coming out. The quantity we study is same mass, so same mass. For the same time delta T, areas might be different. This is A1 and this is A2, and the velocities are going to be different, V1 and V2. But we know according to principle of continuity, A1 V1 is equal to A2 V2, which is equal to, we can say, AV. So that also has become a constant. But what only difference you should remember is kinetic energy and potential energy are produced, and because of you do the work, and again express the work in terms of pressure. Why? Because we are expressing in terms of area. That is the reason we are using that. You see beautifully, AV delta T, AV delta T, AV delta T, AV delta T remains constant in all the things, right? So now what we will do, I can take that AV delta T, I will divide the whole thing by AV delta T. Then what will happen to the equation? P1 minus P2 plus half is equal to, sorry, work done is equal to half rho V2 square minus V1 square plus I have here also rho is there. Rho is there or not? Let me cross check little. Yeah, rho we have. Yes, rho is there. Rho 0, 0, 0, right? AV delta T is gone. H2 minus H1. Okay, this. Now we will spread it. P1 minus P2 is equal to half rho V2 square minus half rho V1 square plus G rho H2 minus G rho H1. Then I think we can collect term 1 together. P1 minus comes this side plus half rho V1 square minus comes this side plus G rho H1 is equal to P2 minus P2 comes this side, P2, this is there plus only half rho V2 square, then this term H2 plus G rho H2. Okay, P1 half rho V1 square G rho H1. Variable you see 1 and 2, only H1 V1 P1 is changing, P2 V2 H2 is changing. So we can write simply dropping the subscripts P plus half rho V square plus rho GH. It will be better to write instead of 0, 0, I am getting confused because usually we say rho GH. So rho GH is a better term, that is equal to a constant. Yeah. So dear students, ultimately we have reached P1, P plus half rho V square plus rho GH is a constant. This is the Bernoulli's principle. We have proved Bernoulli's principle. I hope you understand. Yes, it will come by practice. Dear students, again and again I repeat only one thing. Yes, I have made as usual, I show you. Why? Because I may have 35 years of experience in teaching physics, but it is not possible to remember. Every time you need to think, new ideas are coming. So we should be very clear how we learn. See, again I have made Reynolds number notes. Then I have come to the different energy. Yes, energy of a fluid. Then Bernoulli's theorem. This I have copied. I have noted. When I was studying it, I found that A1 V1 is equal to A2 V2 is equal to AV. You look at many books, majority of the books are using with the subscript and cancelling at the end. What I did, I cancelled it, I made it equal in the starting, so it becomes easy. AV delta T, AV delta T, AV delta T. The less we have subscripts and symbols, it is more better for us, easy to remember, right? And I have solved it. And also you see this which I have completed. I want to say, I see here one point is there which I would like to include here, which you will not have later any doubt. The same thing, I am just going to divide by something and give you the final formula, right? See, this is what is the final formula, another form of the formula. Okay, the same thing, another way you can write the same formula which I have discussed earlier. See, I should remove this also. Okay, right, this again. P plus rho half rho V square plus rho GH is equal to constant. Okay, now let us divide it throughout by rho G. Yeah, P by rho G plus half V square by G plus H is equal to, this thing will go again, it includes all in the constant, okay, constant. And this is called pressure head, and this is called velocity head, and this is called potential head, potential head. So this is another way of expressing the same Bernoulli's equation. Okay, sorry. Okay, now this I have done it. In the coming videos I will shoot about surface tension, capillarity. Then you will find that we have completed fully all the things, theory related to properties of fluids, right? First we started with hydrostatics and moved to hydrodynamics, and we would have completed, and later I will do numericals. I am focusing first on only theory, and next I will do numericals. Thank you so much.